your address in chat. Don't admit to any crimes like usual. I'm gonna go ahead and share my screen. Y'all can see this, right? Somebody? Okay. So, first thing we're talking about today is trees. Well, that's kind of the main topic of today. When it comes to trees, there are a few subtopics that I think are pretty necessary to understand. So, let's get started. So, a tree, at its most basic form, is like a linked list where every node has potentially more than one connections, right? Whereas for linked lists, it's linear. The nodes will only point to their successor or their predecessor. With a tree, you might have a structure where one node might point to however other many nodes, and it's traditional that the nodes don't point backwards. So as you can see in this little diagram right here, we've got a linked list, element 1 pointing to element 2. Whereas trees, we can think of a parent-child structure as kind of being like, that's the paradigm. So think parent node points to children nodes, and then these children in turn have the opportunity to then have their own children. So some terminology that y'all are going to need to know. For trees is, represented in this diagram right here. So the root node, obviously being the highest node in the tree. Y'all are going to learn at some point the topic of n degree. N degree essentially means how many connections are going into this node, right? So as you can see, P would have n degree of 0 because nothing points to it. Would have an out degree of 2 because it has 2 connections. So looking for a root in a tree, it's the root, it's like the source that you start from. Nothing is before it. So that's important to identify the root node. Children are also connected in a similar way as the root node is, and as you can see, the tree is a self-similar data type. So in this example, P is a tree, whereas everything below P follows that kind of paradigm. Q is also a tree. It's known as a subtree. A is a subtree. L is a subtree, so on and so forth. That's denoted by this little triangle right here. Any way that you can block off a node and its children and children of children is also going to be a tree. And I make this point because intuitively, I hope that's going to help you understand why recursion is maybe a good way of understanding trees and such, because if we have a self-similar data type, it makes sense that we would call the same function over and over and over and over again, right? Like if we defined a function for P, that function would also probably be useful for Q and A and L and so on and so forth. Nodes that have no children are called leaf nodes. As you can see, they appear at the end. Family tree relationships that you would see on a regular family tree also apply here. So A and B would be siblings. I guess there's you could have uncles or cousins maybe. I don't know exactly where that would be on this tree. And the height of the tree is just denoted as the amount of edges that it takes to get from the root to the child. And depending on the assignment or potential test question, they might ask you to count this differently. Some people are going to say you count the root node and then you don't count the leaf nodes, or so on and so forth. I would say that this is a tree of height 1, 2, 3, 4, 5, I would say. But again, you would just have to consult whatever governing authority has made your test questions. Okay, binary trees. So if we just defined trees to be this abstract data type where it's kind of like a hierarchy, and the hierarchy kind of starts at parents and goes down to children until you reach leaves, that's like rectangles, and binary trees are like squares. So binary trees are still trees, they just have some extra rules. Specifically, rules that you need to preserve in a binary tree. The most important one, binary, hence 2, is that each node can only have 2 children. So you can see this tree right here, this example is not a binary tree because the C node has 4 children. It'd be like a quaternary tree or whatever syntax describes that. Whereas this bottom one, this is in fact the valid binary search tree. Also, something that's important to note for a binary search tree specifically is that order, relative like Boolean operations have to be preserved through the whole tree. So what does that mean? As you can see, this node 60 right here, anything less than 60 must appear as a left child of 60, and anything greater than 60 must appear as a right child of 60. And as you can see, that the order is preserved everywhere in the tree. You look at 41, 16 and 25 are all less than 41, 53, 46, 55, 42, all greater than 41. Same thing over here. Everything to the left of 74 has to be less than 74, and so on and so forth. So when you're thinking about a binary search tree, you have some rules, like at most 2 nodes, and all of the nodes have to be sorted. So kind of a delicate substructure, I would say. But it's good to know how these things work. Oh, also, by the way, this is going to be the topic in PA4, so y'all are getting a little bit ahead. So some terminology. We already talked about the root node. We already talked about leaves, parents, and children. I'm going to spend most of today talking about traversal. As a little introduction, traversal just means like if we have this structure right here, you know, this data structure 5, 2, -4, 3, whatever this mess is, we can represent this in a few different ways. Like specifically, if I gave you these nodes and I asked you like, represent this tree as a string of nodes, like one line, how would you read in essence this data structure? Like how would you print this, you know? And as we're going to see today, there's like 3 or 4 different ways to do it, kind of depending on how you classify them. Okay, searching. This is, as you can see, a little excerpt from a node search algorithm. So essentially the base case is you find what you're looking for, or you've reached the bottom. And otherwise, if, you know, depending on what you're looking for, if it's to the left, you search to the left. Otherwise, you search to the right. This is a binary search. It's done recursively, hence binary search tree. So imagine we were looking for node 3. We would first call search on 5. See, for our base case, we haven't reached null yet, and 3 is not 5, so we're not here. And let's see, 3 is not greater than 5, so we're not here. We would end up searching the left tree, so now we're searching node 2. And then as you can see, we would search 3 and we found it. So again, not really the topic for today. Good to know, but we're gonna have plenty of time to think about this later. Insertion and deletion. So y'all are gonna think about this quite deeply in PA4. So I don't feel like I need to cover it in great detail, because you're gonna have, you know, plenty of opportunity to really get this nailed down. But when I say that a binary search tree is a delicate data structure, that means you have to preserve it at every state. So every time you do an insert or every time you do a delete, you're going to have to make sure that you didn't just mess up the very delicate balance that you need to have to make sure that this binary search tree is still valid. So inserting a node, you pretty much always want to insert as a leaf. So specifically in this example right here, it looks like we're inserting 95. So an insert to a binary search tree is it's not linear time. And it's not constant time, it's log time, because you have to find where you're going to insert this node. So imagine we have 95, and we want to insert 95 to this tree. Well, first we have to start at the root, and then as you can see, we work our way down and we find a position that is suitable for 95, a place where we can put this node and not break the structure. Again, I don't want to talk too much about it. It's like a little too advanced for today's purposes. You're gonna have plenty of chances to look at it when y'all get your hands on PA4. So deleting a node is a little bit more sensitive than insert, specifically because insert, you can just always assume that you're looking for a place to put a node and just kind of always put it as a leaf, not really messing anything else up. An erase, you could potentially be erasing a node that is important for the structure of the rest of the tree. So as you can see in this example, if we were to delete 60, that wouldn't be a big deal. If we were to delete 80, that wouldn't be a big deal either. Deleting a node like 70 would be more so a big deal, because now we've got to have something to replace it. And then deleting 50, again, is more so of a big deal because we have to maintain these connections. Really, it's not too difficult to understand what's going on here once you've actually coded it yourself. Before you've gotten there, I understand why you might have some confusion. Specifically, when it comes to erasing a node that has children, you have two options. So as in this example right here, if we're deleting 50, you can either replace a node with the maximum element from the left subtree or the minimum element from the right subtree, if that makes sense, right? So in this example, the maximum element from the left subtree is 40, and the minimum element from the right subtree is 60. And either one of those will do to replace 50, right? Because the rule is that everything on the left has got to be less than this node, and everything on the right has got to be greater than this node. So if you pick 60, you know for a fact everything else on the right side of the tree is greater than 60. So 60 works here. And you already know that 60 is greater than everything else on this side, right? Because, less than 50, greater than 50, this must be. If you pick 40 here, then you know that this 40 is greater than everything that could potentially be on the left side of the tree. So you've got two options. Like, in this diagram here, the one down at the bottom, if you were to delete 10 per se, you could replace 10 with the maximum element from the left subtree, which is 9, or the minimum element from the right subtree, which is 11. So again, a little bit too advanced for our purposes today. Insert and delete, you're going to have plenty of time to think about that in PA4. So tree traversal, this is really the main topic that I want to get to today. I kind of struggled to give you a conceptual understanding of postfix and infix notation, I think 2 weeks ago, and I said, just take my word, this is going to make so much more sense when we go to trees, which I will actually be explaining that today. Has to do with tree traversal. So imagine we've got this tree structure right here, and I asked you, how do you print this, right? Like, this is pretty abstract, right? We just got a bunch of nodes that are just kind of pointing to other nodes. It doesn't seem to be any intuitive way to just represent this as one list of numbers, right? I mean, theoretically, this is one list of numbers, but how do we represent that? Well, there are three kind of like different approaches that you could take to this. So the first approach that you could take is something known as pre-order traversal, or pre-order, in this case, pre-order print as it's defined. And that would print the nodes by visiting a node, visiting its left children, and visiting its right children, right? So the idea behind pre-order traversal is if you were to print this tree, you just one node at a time, you would print the node, and then recursively call print nodes on the left and recursively call it on the right. And as you can see, that's defined here. First thing we do is we print the value of the node, and then we make a recursive call. Pre-order print was the function we define here. So this call is recursive call to the left subtree, recursive call to the right subtree. And as you can see, that's going to end up looking something like 8, 3, 1, 6, 4, 7, 10, 14, 13, right? So that's maybe not too difficult to understand, right? The idea being you print the node and then you visit all of its children, printing them along the way. I think the most intuitive way to represent a tree is to just flatten it. So imagine if you were to read this consecutively left for right, as if like the hypothetical like y-axis here didn't really make any difference, right? If you were to just read these like on this x-axis, you would get 1, 3, 4, 6, 7, 8, 10, 13, 14, and maybe it's a little bit difficult to see in this diagram that geometrically like that is x to y, because it kind of looks like 10 and 13 might be on the same like x value if you had an axis here. So the way that we operationalize this and make it formal is called in-order traversal. This one is my favorite. I think it's the most intuitive. And essentially the algorithm here is a recursive search on the left subtree. Once you've finished your recursive search, you print, and then a recursive search on the right subtree, and then the algorithm is done. So as you can see, we start at node 8, we recursively search all the way left until we get to 1. 1 would be this call where it would be making 2 calls to null pointer, which would do nothing. You would print 1, and then let's see, the recursive stack was at 3, so you would print 3 and then traverse right, Now you're at 6, so you would print 4, 6, 7, print 8, so on and so forth. Again, I apologize if I'm just kind of like randomly or seemingly randomly listing numbers here. I promise I will go through this in more detail. The last algorithm, I think, which is the most tricky, probably the least intuitive, is called post-order traversal. So specifically, starting at the root node, you visit all of the left subchildren and all of the right subchildren, and then once a node has had all of its children visited, that's when you can print it. So you start at 8, 3 to 1. You visited all of the potential subchildren of 1, so you'd print 1, and then you still need to visit some subchildren for 3, so 6, 4, and 7, 6, 3, and it would be 13, 14, 10, 8. So again, if that's confusing, I apologize. I will be explaining it, I think, hopefully much more thoroughly today. The rest of these slides are about an Euler tour, which I think is kind of unnecessarily confusing for our purposes. So if y'all are interested, y'all can come back and look at this. I don't think you need to know this. Yeah, I do not think you need to know this. So that being said, I think that's all I have for the slides. I'm gonna do some examples in front of y'all. So have I lost anybody? Everybody still with it? We got
My question is just why would we use those specific types of search algorithms? I
like
mean,
the
we're not really getting them from least to greatest. What output is really giving us?
so like as in the traversal algorithms, why would we use the different traverses?
Yeah.
That's a good question. So, actually, I'm gonna go back to sharing my screen. Uh, okay, so depending on what your purposes are, one of these algorithms might be suited to like actually accomplishing something. So I think to your point, it's going to be rare that we want to print the nodes. So this is kind of like a very specific example here. Like probably not going to be an instance where your only goal is to just print 8, 3, 1, 6, 4, 7. But there are instances in which actually visiting these nodes in a certain order does make a lot of sense. Like, I guess print would make sense for in order print. So to your point, if you wanted to get all of the nodes in ascending order, you'd have to do in order traversal. You can see that's only true when you have a binary tree or a tree that's sorted in such a way that like all of the nodes on the left are less than, and then all of the nodes on the right are greater than. If that's the case, then an in order traversal is going to be like you said, this is your sorted output right here. But imagine instead of printing, like instead of this being a print statement here in the middle, this was a function call or some type of logic, right? And maybe I glossed over this, but really what I'm trying to nail home is that depending on, so this right now it's print. Assume it's just some abstract function call, right? So depending on where you put your function call relative to your recursive calls, this is going to give you different orders in which you traverse the tree. So imagine instead of print here, it was delete, right? It would be a poor idea to use pre-order traversal if we were trying to delete all of the nodes in our tree, right? Like imagine we have this tree and we're defining the destructor for that tree, and we want to be able to delete all of the nodes, and we call delete nodes on node 8. So the first thing we would do is we would destroy node 8. And then now what, right? Because we've got this function delete nodes 8 left, but 8 has been destroyed. So 8 is completely gone. There's nothing we can do here. So depending on the
So it'd be
function,
like deleting. It would be like deleting the head node, and we'd lose access to the rest of the list.
yes, exactly. Which is
Okay.
this is an instance where you would need the functionality of post order traversal, right? Because specifically post order makes the function call only when you are guaranteed that you've seen all of the potential children, right? Like I kind of did gloss over this, but like when I say like you print a node only after you visited all of its children, if you're trying to delete, then this is the algorithm that you want to do, right? Because like you don't want to delete a node until you're sure that you've seen all of its children. So specifically, if we were following post order delete, we would be deleting in this order, which I think is a little bit more intuitive, right? Like you'd want to delete 1, 4, 7, 6, 3, 13, 14, 10, 8. And that would be safe, right? Because you haven't deleted anything that contains information about the rest of the tree that you then need. Good question though. Excellent question. Does that kind of like
Yeah, no, that makes sense. That makes sense.
cool.
Thank you.
Yeah, of course. I maybe could have prepared like more concrete examples of like this is when you use this case or this is when you use that case. But excellent question. I definitely should have considered that. When I teach this next year, I'll have that ready to go. So let's see. I'm gonna share my screen again. I'm gonna do an example in front of y'all. Just so that y'all can see it happening. Let's see. Can y'all see my iPad? Is that
Yeah.
okay? Cool. Also, I can't really see chat at the moment, so Oma will be more than happy to take care of your questions if you have them. If you want to stop me and you want me to draw something, please unmute yourself. So let's draw a tree just for fun. So imagine we've got a tree that looks like this. And we've got some nodes here. Right, and nodes can be anything. So the data that we've just put here, I'm not going to say it's like completely meaningless, but for our purposes, this is not a super meaningful piece of data. And the question I asked earlier was if you had to represent this whole structure as one string or one line, what's the best way to do that? And I defined earlier, there are 3 different ways that you could traverse a tree using recursion that are kind of, relatively more or less intuitive. So there's a pre-order, which I'm going to do on this tree just to, show you what it looks like. And I'm going to kind of on this side, I'm going to kind of show what's happening with the recursive stack, just in case anybody is not entirely clear what's going on. So we defined down here pre-order, define pre-order to be something like this. So you call pre-order on node, and then first you do print of the node, and then you do the recursive call to the left. So pre-order node left, and then you do the recursive call to the right. And you would need some kind of edge case to handle the base case. So assume like this is it's not null pointer, but I don't think I need to write that for this purpose. So this is kind of generally the algorithm we're following. So let's see. First thing we do is going to be pre-order A. And then to calculate pre-order A, first we do print A. So that's going to add to the string down here. And then we do, looking at our algorithms, this happens first, this happens second, this happens third. So we've printed A. Now we need to call pre-order on the left subtree. So now we're calling pre-order on this tree. So pre-order B. So we print B. And as you can see, the next step after we've printed B is to call pre-order on B's left child. So pre-order D. And as you can see, D has no subchildren, so all we need to do here is print D. So print D, and then we're going to call pre-order on E. Print E. So now we're finished here. Now that we've done pre-order for B, we can print A. So print A, and out of consistency, let me go ahead and add the nodes we printed. So we printed A, printed B, printed D, printed E, A, and then see, after printing A, we already printed A. I'm so sorry. I'm so sorry. I'm totally tripping. So now we do pre-order on C, and then looking at this subtree. So first we print C, and then pre-order on the left child. This, so we print 1, and then as you can see, it's just going to be 2. so on and so forth. So hopefully this will give you all some intuition about what the recursive stack is going to look like, kind of. I messed up by accidentally putting a print A statement here. I got a little bit ahead of myself. That's going to be the next one. So I hope this kind of makes clear what happens. Like essentially when we define our function in this way, we're saying number one is print the node. And then by putting this next recursive call here, print node, we're actually guaranteeing that we're going to visit all left nodes by putting this here, all left nodes. So specifically in the case where we call a pre-order on A, we're guaranteeing that we're going to see all of these left nodes before we even make it to the next part of the function. So if this was 1, if print was the first thing that happened, visiting all of the left nodes is the second thing that happens, and visiting all of the right nodes is the third thing that happens. So visit all right nodes. And that's just a peculiarity of the way that this recursive function happens. And then, obviously, as y'all can see, the different permutations in which you put print, or, really this is just any kind of function, is going to change how the tree traversal actually shakes out. So I'm going to go ahead and redraw this tree and do another traversal. So we had what? It's like something like this, I think. Apologies if that's not correct. So our in order traversal is just going to essentially be flattening the tree. So let me draw this better. That way it's more obvious what's actually happening. So for in order traversal, this one's my favorite because I think it's the most intuitive. It's the most easy to understand what's actually happening. So as you can see, if we were to just read this tree left to right, you'd be able to see pretty quickly that the in order traversal is just, pretty geometric, like as in we got D and we got B, E, A, 1, so on and so forth. As you can see, the order in which they appear left to right is the order in which in order traversal is going to read them. So in this case, it's going to be D, E, E, A1, C3, 2, 4. Again, so this is pretty simple. And this is going to be characterized by a function where your function call would be the second line, not the third line. So def in order, and I'm just going to speed run this. So first we do in order left, and then print node, and in order right. And then as you can see, we've switched our function call to the middle, and that is the distinction between in order and pre-order. Our function call was first for pre-order. Our function call is going to be in the middle for in order. And then you guessed it, for post order, it's going to be last. So I'm going to draw this tree one last time. So for post order traversal, I'm going to maybe like draw some arrows for how you would evaluate this, because I think this one is the least intuitive. So you start at A, and the paradigm behind post order traversal, I'm going to go ahead and write it here, is that you have to visit all of the children before you allow yourself to do the function call. And we'll see post order node. And again, sorry for the time it takes to write. Just gonna speed run this. So post order left. I'm gonna do post order right, and then print node. And again, like I said before, this could be any function call. The example I gave earlier was that this could be like deleting. This could be your destructor. So this could be like, you could think like delete or whatever it is. But yeah, so the main distinction between all of these algorithms is specifically where your function call is relative to your recursive calls. So There you go. So let's go ahead and run this. So we're going to start on node A, and we don't print node A until we've seen all of its left children. We don't print B until we've seen all of its left children. We get to D. D has no children, so we can print once we have seen all of the children. Well, there's no children, so why even bother? Start with D. Now recursively, let's backtrack up to B. We can't print B yet because we haven't seen all of its children. So now we got to look at E. E has no children, so we're good. Backtrack up to B. B, we've seen all of its kids. We've seen D, we've seen E. So now we can print B. So that completes the left recursive call to A, and then we still can't print A because we haven't seen all of its kids yet. So we have to visit C, and we have to visit 1. So let's print 1, back to C, print. We can't print 2 yet because we have to see its kids, so we have to go to 3, and then back to 2, got to see 4, back to 2, back to C, and then back to A. Okay, so if I made like a small mistake and one of these letters is off by like a little bit, I apologize sincerely. But I think that should give you like an intuitive idea of what's happening here. Really, for the difference between pre-order, in-order, and post-order is where this function call is relative to the recursive calls. So these are the recurse. And as you can see, there's 3 different ways to do this. And even though this tree is actually, this is the same tree as both examples, same tree, we're going to have different different outputs depending on, as you can see, these 2 are not the same tree, different outputs depending on the traversal algorithm. So that's kind of the intuition here. And how does this actually become useful? So in week 5, I kind of briefly talked about postfix notation. So I think I remember showing y'all this equation. Let's see, it was something like A times B plus C minus E divided by E. And I kind of waved my hands in the air and I just said, take my word for it. Postfix is equivalent to infix notation if you understand expression trees. So real quick, I'm just going to speed run. And I'm going to speed run postfix to infix just to get the infix form so that I can prove my point here. So the algorithm to go from postfix notation to infix notation is you use a stack. So let's represent that as, actually draw the stack here. And we've got, so many addresses. So this is our stack. And the algorithm is pretty simple. So the idea is when you reach an operand, you push to the stack. Oh no, I'm so sorry. Oh man, I'm so sorry. Total blunder. Where was I? This was the infix. Yeah, if y'all are still tracking with me, I deeply apologize. I always screw up somewhere. Okay, this was the infix, and I wanted to show y'all how you would get from postfix to infix. So let's move this down a little bit. Okay, so the postfix notation that is equivalent to this is, I think, I'm doing this off of memory, so I think it was AB star C D E. Oh, give me 1 second to think. I'm sorry. I'm doing some mental math here. Minus. Okay, yeah, I'm pretty sure. I'm like 90% sure. So this is gonna be your postfix. Okay, so I'm gonna real quickly recap the algorithm from going from postfix to infix. And the algorithm here is when you reach an operand, you push it to the queue. When you reach an operator, you pop the last 2 operands, and then you push the result back to the queue. So I'm going to walk through this relatively slowly so y'all will get a chance to see it happening. So we start with A, push it to the stack, and then Now we're looking at B, push it to the stack. And then now we reach this operator. And the rule for an operator is you pop two things off the stack. So we're gonna pop B, we're gonna pop A, and then we're gonna apply the operator, which is multiplication. So A times B, and then we're gonna push whatever this was back to the stack. So go ahead and do that. So pop two, and then push A times B, and then the C. So now we just keep going. So we reach C, push D, push E. I hope all of those things are fair. Now we run into an operator. So we pop two and then push the result, which is going to be this. And then now we run into this operator, and then we pop two and push the result. Let's see, it's going to be, and then we run into our final operator, which is here, and we just pop two and push the result. Mapping. Okay, so I kind of briefly went over this in week 5. I didn't actually have a way to do it in front of y'all, so hopefully this kind of clears up how you do. I'm gonna label this. This is what this is. Postfix to infix. So just as kind of a review how you get from one notation to the other. Does anybody want to see me go the other direction? Anybody real quick want to see me do instead of postfix to infix, infix to postfix? Like this direction. You're gonna have to unmute yourself if you want to see this, because I can't see chat at the moment. Okay, well, I assume nobody wants to see it. It's just kind of more math. Y'all have seen enough math. Anyways, so the reason I bring this refresher up is because look what we have here. So this right here, these are two different ways of describing the same thing, right? We have agreed that although these are two different notations, they represent the same equation. Hopefully, I have built y'all's intuition to the point where y'all have now gotten a funny sense that what I showed you here is in some way connected to what I showed you here, right? What I showed you here is that even though we have the same exact tree, so the same tree here, same tree here, and the same tree here, we have come up with 3 different notations for describing that tree. The trees are identical, the notations, this notation, and this notation, they all have the same characters, but they're in a slightly different order. Now, back to here. Y'all's intuition should tell you we have got the same expression. 2 different ways of reading that expression should clue you in that this, in reality, is a tree. And that the difference between these 2 expressions is just the order in which we traverse this tree. So if this is our infix notation right here, what does this tree look like? Well, we know that A multiplies with B. We know that D gets divided by E. We know that C minus D appears in this equation. So we got C minus D. And then we know that, hang on, y'all, let me rearrange this. We know that these things get added together. So this is our expression. So the last few minutes of us catching up on postfix and infix, really what we were doing is traversing this, what is known as an expression tree. Okay, so with an expression tree, I hope I haven't lost anybody. I know this is a little bit confusing, a little bit. Let's just take this one step at a time. So an expression tree is a way of visually representing what an expression in mathematics looks like as its pure structure, right? So without worrying about the traversal or the interpretation, being either infix or postfix in this case. This is just mathematically, this is the structure of what we're looking at. I'm gonna delete these circles. That's pretty. As you can see, the rules in the tree are as follows. All leaf nodes must be operands. So as you can see, all of the leaf nodes, being these 5, are operands. Operators must have operands as children. So as you can see, our operators, being these ones, have all got children. Well, an operator could have 2 operators as children, because these are gonna evaluate to an operand at some point. And then, as you can see, we evaluate the expression by essentially working upwards through the tree. So this is D for E, this is C minus D over E, this is A times B, and then this one right here this is everything put together. So A times, oops, my bad.
So how can we detect which one is the root of the tree? Is like in this case, is it the plus or operand? Is like how can we detect it?
Yes, excellent question. Excellent question. I was waiting for somebody to ask, so thank you. Specifically, what's not shown here are a lot of implicit parentheses, because every time, so when we were evaluating the stack, remember we had something that looked like memory serves, and it might not. Memory might be failing me here. C, D. So remember when we were here in the expression, and I just wrote down D divided by E. Well, technically, to make this completely accurate, you would have to be adding parentheses at every operation, right? So you would have to be preserving the order of operations using parentheses. So in this case, it'd be C minus D. And then finally, I'm just going to write it down here to the side. So we got A times B plus C. Right? Does that make kind of some sense? You can see that the root node is going to be in the middle of these parentheses. So no matter what this expression tree is going to look like, it'll always look like some left expression, and then we got some kind of right expression.
Yeah, that makes sense.
And then if we're trying to search for this root node, we know it's going to be the one that's in the middle of these 2 parentheticals. Does that kind of answer it?
Yeah. That makes sense,
Okay.
man.
Excellent question. Excellent question. Whoever asked that, you're on the ball. I'm sure other people were wondering that. So thank you very much. Very much appreciated. Excellent. Okay. So where were we? So as intuition serves, and our examples before, when we have a tree, the way in which we traverse that tree, the order in which we traverse that tree is going to be very impactful for the output of the traversal. Like I said before, the output, this could be a function call, so you could be deleting nodes, you could be printing them, whatever it is, whatever, it doesn't really matter. In this case, we're doing math, so we're doing like a math evaluation. But just to get the output of the equation, let's just say that we're printing for now. So technically, if this is our expression tree that we just defined here, we can come up with 3 different notations to describe the same expression. So we've got like prefix notation, and I don't think in this class we ever touch this at all. I don't think. We've got infix notation. So y'all don't freak out seeing this stuff. Because like once you've seen that it's all trees, it's really not that bad. So and again, as intuition serves, we've got pre-order traversal, in-order traversal, and post-order traversal. What do you know? We've got prefix notation, infix notation, and postfix notation. I wonder if there's some correlation between the two. Well, obviously there is. Depending on which tree traversal algorithm we use, we're going to get a different notation. So let me go ahead and move these over, give myself a little bit more room. Yeah. Okay, so prefix notation would be a pre-order traversal of this tree, which, as we can see, would be something like this. It'd be like plus times A, B minus C. I think. If I'm off by like a character and y'all notice it, or if you happen to be watching this video later, don't trip. I hope y'all at least get the idea. I am prone to mistakes. Okay, so this is prefix notation. Infix notation would be, remember I said for infix, the best way to think about it is just flattening the tree, like left to right, flattening the tree. So let's just do that here. So we got A times B plus, and I am going to add a parentheses here. Remember, like I said, technically there is a parentheses at every level. They're not always necessary to, like, sometimes the order of operations will preserve the order for you, but in this case, I do need to add a parentheses to just make it look a little bit nicer. And this is our in order traversal, right? Because we've going left to right, we've got A times B plus C minus D divided by E. Right, that was our in order traversal. And then for post order traversal, again, the rule of thumb here is that you perform the function only after you are 100% positive that you have visited all of the children of the node. And in our case for delete, that's important, right? Because you have to see all of its children before you delete the parent. So in this case, we would start at plus, we'd work our way down here to A. We've seen all of A's children, so we backtrack to star. We look at B. Now we've seen all of star's children, so we can push the star. Back up to plus. Now we have to search this part of the tree. We get a C here. See, now we're searching division. We get D. Back here, we get E. Back up, we get division, subtraction, and addition. So as you can see, specifically, I'm going to move these a little bit. Those notations that were like super confusing in week 5, like, oh, what is infix? What is postfix? Now it's pretty tame, huh? Now this is like, I think relatively not that scary anymore. As y'all can see, this is what I wrote up here. Infix, postfix are really, at the end of the day, just different traversals of the same tree. So I guess the main takeaway from this is that if you're ever confused and you want to know, like, did I do my infix to postfix right? Just draw this tree, draw this tree, traverse it the different ways. You can easily jump from postfix to infix. Really not that much effort. You can verify that your solution is correct. I think not only that, but this should give you some intuition about why you would use infix and postfix, what these things actually mean. Yeah, I mean, if I hope I didn't lose anyone again. I think this is the hardest concept I've covered so far in a weekend review. So if you were able to track through all of this, bravo. There's a little summary of what happened. Oh, I'm so sorry, y'all. So in the first example, I drew the recursive stack. This is actually present with all of the traversals. I just decided to be explicit for this first one. In order traversal, you can just kind of visually see how to traverse this. And you could do a recursive stack to figure this out, but I think the visual proof is just your easiest option. For pre-order, I think the easiest way to think about this is like backtracking, and kind of the rule of thumb is you've got to see all children first. And the main takeaway between these traversal algorithms is that where your function call is in order. So if your function call is first, you're doing pre-order. If your function call is second, then you're doing in order. And if your function call is third, then you're doing post order. And that has a big impact on what actually happens with your algorithm. And then we reviewed infix and postfix notation. This was the postfix to infix algorithm. So just a refresher on that. I skipped the opposite direction. If y'all want to see me cover that, maybe in the exam review, I'd be happy to. And then we proved that infix and postfix notation are really just different ways of describing this structure, which, by the way, this is called an expression tree. Okay, so hopefully y'all's understanding has made some kind of jump. That is the hope. Any questions? Let's see, exception. Or any confusion to clear up at all? Okay, well, let's see. Okay. I think that does it. Thank y'all for showing up during the break. I appreciate the grind like always. It's good to see some faces. If y'all don't have more questions, I assume y'all got it. So y'all are free to go. I'll see y'all next weekend.